Um, the notation that we use is, of course, this. We put this arrow above, so we have a vector v, and we put a little arrow above it to denote that it's a vector. This is what how I'm sort of used to doing vectors and did when I learned it in school. But you also often today see just a letter that's bold instead, and that's also usually to denote that something is a vector, not a scalar value. But I like the arrow better. It's more clear, I think. And then we have stuff like some identities. Like now we want to draw like a zero-length vector. It's draw a dot just to have something, but really we shouldn't be able to see it at all. And we call that. We can write like this: 0 or O with a vector notation. Like this. Oops. I'm just going to put the word here as well. And we have another thing, another identity, which is unit length vector. So if I have a vector like this, and its length is 1, this is called a unit vector. Also, unit length vector or unit vector. And these are quite important in many operations. And we also normalize vectors to turn them into unit vectors to keep the direction, but to change the length to 1. Okay. Just. I'm gonna save these as well, so you can look at them if you want later. Okay. So the basic operations we can do on vectors. Simplest one is addition, vector addition. This is really sorry. One more. Yeah. So suppose we have two vectors, we want to add them together. How do we do that? I'm just going to quickly draw two vectors. Well, this is geometrically how we add them together. We simply put one at the end of the other. So we call this vector u and this v, just for notation later. Like this. Just take a different color here so we can see the difference. The resulting is result is a vector. So this is the purple thing is the result of the addition. So it's like u plus v. And that's what it means to add vectors in a geometric sense. And there, of course, as any mathematical operation has some nice properties. Commutative property, as we call it. It means that we can do it the other way around, and then we still get the same result, just like with numbers. So we add two numbers together, we can swap them, and we get the same result. I'm just going to draw what that is in geometry, like this. I have u and v. Another color. So we do the other way around. We start at the same place and we put the other vector first. Oops. And then the second vector. And we get to the same place. That's the point. uv vu. There. The other one is associative. The associative property, and it's slightly less intuitive, but it's equally important. Associative property. Yeah, it's a little more involved, but it's not that bad. So suppose we have 3 vectors. And it just means that we can put the parentheses at any place and we get the same result. So like this. And it's actually quite intuitive if you look at it. If you look at the geometry of it. So we put like 3 vectors here, like u, come up with another vector v, and a third vector w. So if we start with this v plus w, I'm just gonna pick a different color here for that. Yeah, just a minute, just put these as well, just to make it more clear what's going on. This is u, this is v, and this is w. There. Okay, u plus v is of course here. So if we take u plus v and then add w, then we end up here. Pretty obvious. On the other hand, if we then try to draw a v plus w in the convenient place, of course the place doesn't matter, but it's easy to see like this. Well, the intuition of it is pretty simple. Is that we can do this, and we can do this. We can perform this calculation first and then this calculation, or we can start with the first plus and then do the second plus, and we still get the same result. So that's the associative property. Yep. Alright, I'm going to do one more, and then we're going to do something else. For a bit. So what was that, 66%? Yeah, it's just another basic operation. So addition is one basic operation. Another basic operation is scalar multiplication. We can multiply any vector by a scalar. A scalar is just a number, is what we normally denote a number. Now we have something called vectors. We need to distinguish between the two. Yeah. Put a little arrow here. So we have a vector v, and we can multiply that by a scalar. We call that a. And what that does is it simply changes the length of the vector. The direction is the same after the scalar multiplication, or the opposite if it's a negative number, but the length is usually at least different. So we have a vector here, and we multiply it by a, then it will become a different length. So I'm going to illustrate that by doing something like this. changes the length of V by vector A. This is what it does in geometric terms. Scalar multiplication. Change the length of V by factor of A. Multiplicative factor. This is associative. Scalar multiplication is associative, and it means that you can do something like this. There's a music class.
No, we have a production and presentations.
All right. Sounds like a silent movie or something. Just got here. I put an arrow for it because it starts to get a little bit. You have to see what is what. Yeah, that's the point. Associative property. So if we want to multiply a vector by two different scalar values, then we can either first multiply the values by each other and get a new scalar value, and then multiply by the vector, or we can multiply one on the vector and get a new vector, and then multiply the other scalar value. And this will yield the same result always. So that's the associative property. I have to move this a little bit to get room for everything. Move the arrows in a minute. There, okay. Distributive property as before. Yeah, it means that we can do something like this. This basically means that this multiplication can also become this addition can also become like a vector addition, and it will still yield the same results. Quickly put the arrows there. As I mentioned before, you can change the direction with a scalar multiplication. In one way, which is a negative number, the vector becomes the opposite direction. So, just going to illustrate that. How did I do that? Yes. So if we want to multiply a vector by -1, it becomes the same length and the opposite direction, like this. But of course we can also multiply by another negative number, and then the length as well will change. Oops. Like this. So this is if we multiply this v by -2, it becomes something like this. And actually, if we use these two properties together, like we could use scalar multiplication with negative numbers, and we also apply addition from before, then we actually have what is equivalent to subtraction of vectors. So we can subtract vectors from each other by simply taking one vector and multiplying by -1 and adding it. Just going to illustrate that. Yeah, just put in a little formula what I just said. So v minus w, v v plus minus 1 times w.